Hello everyone. If you're watching this, congratulations. It means you've remained at least semi-conscious during our first two lectures and are hopefully getting the nuclear bug, if not now, then soon at least. So far we've covered all the fundamentals necessary to understand the rest of the course content, from the fundamental physics of nuclear reactions, how radiation interacts with matter, and the fundamentals of nuclear reactor design. So you know when I say slow or thermal neutrons, that I mean neutrons that have been slowed down by a moderator. And you will know that in a light water reactor, what's the moderator? It's the water. The water behaves as that moderator. The means by which such moderation occurs, we will cover in Chapter 5 on moderators. But today, we're going to look at radiation damage, and I'll give you a general introduction, the billiard ball-like destruction that particle collisions can have in materials, which we call displacement cascades, how such radiation damage can lead to the formation of dislocation loops, cavities, and voids, and how such damage leads to, for example, mechanical property changes, amongst others. And this will equip us with the knowledge necessary to see how the radiation effects described in the preceding lectures might occur. And with that, let's begin with the basics of radiation damage. So firstly, what does radiation damage mean, and how does it differ from radiation effects? Well, radiation damage refers to the production of defects formed as a result of irradiation, producing physical, chemical and mechanical property changes. And it is in this chapter that we'll summarise the types of these defects and how they arise. How is it different then to the term radiation effects? Well, radiation effects refers to the effects on the behaviour or properties of a material following radiation damage, rather than the actual defects created in the radiation damage itself. Now you can imagine that inside a reactor, with all these fission events throughout the core, that there are a lot of neutron collisions with the structural materials in place. And after a lifetime of operation, a material will have been exposed to an incredibly large number of those collisions. So what does each collision do to a material? Well, that depends on several factors, the most important of which is the energy of that incoming particle. If this energy is, that energy is generally sufficient to displace an atom from its equilibrium site in the crystal structure, because the binding energy of lattice atoms is much lower compared to the energy of the impinging particles. And this allows the atom to be knocked off from its comfortable lattice site, leaving a vacancy in its place, a hole where an atom should be. And what happens to the knocked on atom? Well, it's now an interstitial, and it's travelling through the lattice until it loses enough kinetic energy to come to a standstill. So the first step of radiation damage is when a collision occurs. Kinetic energy is transferred from the incoming particle to the target nuclide, and should the energy transferred be sufficient to displace that nuclide, it becomes the primary knock-on atom. And you create a vacancy and an interstitial. And that pair, the vacancy and the interstitial, that's called a Frenkel pair. Okay, a Frenkel pair just means an interstitial and a vacancy. Now that interstitial, with all that kinetic energy, may itself continue to collide with neighbouring atoms and transfer enough energy to knock them off their equilibrium sites, and them themselves knock on further atoms, and so on and so on. And so what we have is what I like to term a billiard ball-like effect of your white cue ball, like your neutron. Your white cue ball comes in with all its speed and it hits the first ball, which then displaces all the rest of the coloured balls, red, for example, if you're playing snooker. And that's called a displacement cascade. because that's exactly what it is, a cascade of displacing atoms. Now eventually the primary knock-on atom, that being the first atom that was knocked off, so there's only one of those per incoming particle, well eventually that primary knock-on atom, or pKa, will come to rest as an interstitial. And this results in what we will in the following figure see here. As you can see, we end up with a core of vacancies where the primary knock-on atom has knocked off all atoms in its path. And surrounding this core of vacancies is a shell-like of interstitials. So as you can see, a single collision, we present our path of our neutron by the black line there. A single collision can cause a huge amount of damage, with these cascades typically occupying volumes of around 1 to 10 nanometers in diameter. Now, damage rates are usually measured in units of displacements per atom per second, meaning how many atoms across the entire material have been displaced per second for a given neutron flux. And a typical damage rate is in the range of 10 to the minus 9 displacements per atom per second for thermal reactors to 10 to the minus 5 displacements per atom per second in fusion reactors. Fusion reactor first wall blankets, they are subjected to significant damage rates. Now, bearing in mind that reactors operate for 40 and above years, at that sort of damage rate, the material, how is it not completely amorphous, you might be wondering. Well, in practice, those Frenkel pairs that are produced in displacement cascades, they can recombine and restore the equilibrium structure. And so many do. However, some defects will often remain. And over time, those defects that have survived, they'll accumulate to cause what we're going to see as radiation effects. Okay, so that's what a lot of the course will focus on, is the radiation effects. So how can we estimate the number of these displacements? Well, you can model displacement rate, provided you know the displacement energy, i.e., the energy needed to knock a lattice atom off its site. Now, in most calculations, you can estimate a displacement energy or assume an energy of 25 electron volts. And you'll need that number, 25 electron volts, for some of the questions I'll set you in the accompanying problem sheet. But actually, the displacement energy ranges depending on crystallographic structure, the material in question, the trajectory of the incoming particle, for example, a neutron, and the temperature of the irradiated material, because that will dictate the kinetic energy of the atoms before the neutron comes along and smashes into them. And in the figure here, you can see at the bottom, you can see an interesting correlation worth noting of how melting temperature correlates with displacement energy. Aluminium here at the lower end and tungsten at the top, meaning it's harder to displace a tungsten atom than it is aluminium. So what happens if the energy of the incoming particle isn't enough? Well, then the atom isn't displaced, and it instead just vibrates around its position and dissipates the energy as heat. So over time, a material can have each of its atoms, displaced hundreds of times. And as I said, many of the Frenkel pairs will recombine. But what we actually see in practice is that rather than having an equal number of vacancies and interstitials left over in the end, which is what you'd expect, you're producing them, aren't you, at the same rate? What we actually get is we end up with more vacancies than interstitials. And that's a very important point with respect to radiation effects. But why? Why do we get more vacancies? Well, because self-interstitials like to form little stable clusters and are ultimately removed by dislocation glide to other dislocations or features like grain boundaries. But they leave the vacancies. Okay. Not only that, but although both interstitials and vacancies are mobile, interstitials are a little more so, meaning that the centres of the cascades, showed on page 27, are a little more vacancy rich, and that's stabilizing the vacancies, Finally, another point is dislocation climb will play a role, as such dislocations do act as sinks for vacancies and interstitials, but because of the greater elastic strain around interstitials, they're removed just a little more than the vacancies. And all these points come together and mean that we end up with an excess of vacancies. And like I said, that has a significant role in producing unique microstructural features and radiation effects. One of the microstructural features resulting from these cascades are dislocation loops. And radiation will produce dislocation loops at temperatures below around 0.2 times the absolute melting temperature of the irradiated alloy. And these loops form due to the collapse of vacancy-rich cores of a cascade, or the interstitial shell of the cascade. And they will produce different types of loops. Should the interstitial shell condense or collapse onto a close-packed plane, it forms an interstitial loop. Should the vacancy-rich core condense, it forms a vacancy loop. And over time, an irradiated alloy can see a tremendous increase in its dislocation density because of the production of these loops. Now let's take a cubic close-packed metal, say stainless steel. The stacking sequence of the close-packed 1-1-1 planes is ABC, ABC. Now, should we form dislocation loops, they'll disrupt the stacking sequence of those planes, producing stacking faults. Should a vacancy condensation occur, we produce an intrinsic fault. Should an interstitial condensation occur, we produce an extrinsic fault, as shown on page 29 schematically. And it shows the dislocation loops disrupting the stacking sequence of the close-packed planes, with figure A here changing from ABC, ABC to ABC, AB dash ABC, caused by effectively the removal of a layer of atoms, i.e. a vacancy loop. And figure B shows a change from ABC, ABC to ABC, AB dash A dash C, ABC, caused by the addition of an extra plane of atoms, i.e. an interstitial loop, and that causes an extrinsic fault, because we've added that extra plane. Now these dislocation loops are sessile, as in they can't glide, with the Burger's vector normal to the planes and of magnitude equal to the interplanar spacing. And the formation of such loops is why in many materials we sometimes see increases in the dislocation density after irradiation. Of course, it's a little more complicated than this, as I'll show you later on, as irradiation can also lower the dislocation density of a material, should it be highly dislocated to start with. And that's because irradiation will cause a material to reach an equilibrium dislocation density based on the material and the irradiation temperature, but we'll discuss that for specific materials later on in the course, so don't panic about that. So, like I said, the formation of dislocation loops will occur at temperatures below around 0.2 times the absolute melting temperature of the alloy. Well, what happens above 0.2 times the melting temperature? Well, here the main concern isn't dislocations, it's the nucleation of cavities and voids, caused principally by the excess of vacancies we are producing under irradiation. Because of those vacancies, those vacancies are going to conglomerate, and in their conglomeration they're going to form voids and cavities. But not only that, but a number of transmutation products help to facilitate the formation of such features, notably dissolved helium atoms, as this helium helps to nucleate such voids. Why helium? And where does it come from? Well, it comes from the transmutation of boron, nickel, and iron, mostly. because these spit out alpha particles. And since alpha particles are positively charged, they scoop up electrons quickly from their surroundings and become stable elemental helium. And for high nickel content materials, like a stainless steel, the production rate of this helium can be up to 10 or so atomic parts per million, per displacement per atom. So it sounds like a complicated unit there, but yeah, up to about 10 or so atomic parts per million of helium per displacement per atom. Okay? And once produced, these helium atoms precipitate out as bubbles. Okay? So they can form these bubbles, and those bubbles then act as sinks for our excess of vacancies, creating nucleation sites for voids and cavities. And of course, if you've got voids and cavities, you're going to get an increase in volume of the overall material, and that's how swelling occurs. So you can actually get swelling of the material. We'll talk about that later on. Now, without the presence of helium, the rate of that swelling is dramatically reduced, and I'll show you that later on. And that's because the incubation period is extended before you get swelling, meaning that although swelling can eventually occur, helium helps the voids nucleate. Thus, the phenomenon is called gas-assisted void nucleation. And that was first observed in 1967 after a number of reactors had been built and were under operation, and proved actually to be quite a significant problem with a number of components, leading to hardening, loss of ductility, loss of creep resistance should the bubbles form on grain boundaries, and in some cases catastrophic failure. And with that, we complete our second chapter on the basics of radiation damage. Now, in part 2 of this lecture, we'll begin our journey through our list of components, looking at the radiation effects in specific materials used for those components, starting with chapter 3, nuclear fuel, and then we'll move on from that. So I'll see you then for part 2. Have yourself a cup of tea, look over what we've covered thus far, and join us later for part 2.